Imagine silence, the absolute silence of night, when even the rustle of leaves seems loud. Now imagine a silence even deeper, a silence in which there is not only no sound, but also no space to spread it. There is no time to count the seconds of this silence. There is not even the concept of here and there. And in this inconceivable silence, a thought is born. What if everything we see, everything we can touch, all the three-dimensional space around us is just an illusion, a reflection of something completely different, a projection on the invisible screen of the universe? Greetings, my dear listeners. Tonight, we are going on a journey to the very edges of reality, to the place where physics meets philosophy, where mathematical equations begin to whisper about the nature of being. Please write in the comments what city you're from and what time it is. I'm always curious to imagine people around the world listening to these stories on their quiet nights. Close your eyes for the moment. Feel the weight of the blanket on your body, the coolness of the pillow under your cheek. You are lying here in your bed, in your room, in your house. It all feels so real, so tangible. The walls around you have depth, volume. The room extends in all directions, forwards and backwards, left and right, up and down. 3 dimensions, 3 axes of coordinates along which all our lives are situated. But what if I told you that it's all just a projection, that our universe could be a kind of giant hologram where all 3-dimensional existence is recorded on a flat, 2-dimensional surface somewhere on the borders of space? This is not science fiction. It is a serious hypothesis that is being discussed by theoretical physicists at the most prestigious universities in the world. They call it the holographic principle, and it involves something quite incredible. Information describing any volume of space can be contained entirely at the boundary of that volume. Imagine a room. Everything that happens inside that room, every movement of air, every speck of dust in a beam of light, every thought in your head, all of this could theoretically be encoded on the walls of that room. Not inside, but on the surface, on the plane. Sounds absurd, doesn't it? And yet, that's exactly what maths whispers to us as we begin to study the strangest objects in the universe. Black holes, black holes. Even the very phrase carries something primal and frightening. Places in space where gravity is so strong that nothing can escape its embrace. Even light, the fastest thing in our universe, sinks into a black hole without a trace. Imagine such a density of matter, such a concentration of mass, that space-time itself curls inward into itself, forming a vortex from which there is no return. The event horizon is what physicists call the boundary. Once you cross it, you are lost to the outside world forever. In the 70s of the 20th century, the English physicist Stephen Hawking made an amazing discovery. He showed that black holes are not really black. They emit. Very, very weakly, almost imperceptibly. But they emit particles, and gradually, over trillions and trillions of years, evaporate. They named this radiation after him, Hawking radiation. And this is where the problem arose. A problem so profound that physicists are still arguing about it. You see, information in the universe has one important property. It can't just disappear. This is one of the fundamental principles of physics. Information can be transformed, encoded differently, scattered through space, but it cannot be completely destroyed. It's like energy. It changes from one form to another, but the total amount remains unchanged. But what happens to information that falls into a black hole? The book falls over the event horizon. All the information written in it, every word, every letter, every atom of paper, with its exact position and velocity, all disappears to the outside observer. And then the black hole evaporates through Hawking radiation. And nothing. The information is gone. Gone forever. It was as if, in mathematics, 2 plus 2 suddenly ceased to equal 4. A fundamental contradiction that kept the best minds at rest. And then, in the early 90s, the Dutch physicist Gerard 't Hooft came up with a crazy idea. What if, he suggested, information doesn't fall inside a black hole? What if it stays on the surface, on the event horizon? What if all the information about everything that has ever fallen into a black hole is encoded there, on that two-dimensional spherical surface? Imagine a hologram. You've probably seen holographic stickers. They appear to be three-dimensional, but they're really just a flat surface with information recorded in a special way. When light falls on the hologram in a certain way, it projects a three-dimensional image. All the depth, all the volume is encoded in the flat film. 't Hooft hypothesized that something similar happens with black holes. The three-dimensional volume inside the event horizon is an illusion. The real information is stored on a two-dimensional surface. And that's where it gets interesting. Because if it works for black holes, why wouldn't it work for the entire universe? Close your eyes for another moment. Imagine that the entire universe is a huge spherical bubble. We live inside that bubble, or so it seems to us. We see stars, galaxies, galaxy clusters, spread out in 3 dimensions of space. We move forwards and backwards, left and right, up and down. But what if it's all a projection? What if the real information, describing every particle, every field, every event in this universe, is stored at the boundary, at the surface of this cosmic bubble? What if we are holograms? In 1997, Argentine physicist Juan Maldacena, who worked at the Institute for Advanced Study at Princeton, the same institute where Einstein once worked, made a breakthrough. He showed a mathematical correspondence between two very different worlds. On one side is the three-dimensional space with time filled with gravity, described by Einstein's general theory of relativity. On the other side is the two-dimensional boundary of this space, where there is no gravity, but quantum field theory. And these two descriptions are equivalent. They describe the same reality from different points of view. It was like an epiphany. Maldacena had found a dictionary, a way to translate questions from one language to another. A complex problem in three-dimensional gravitational theory might have a simple solution in two-dimensional quantum theory at the boundary, and vice versa. Physicists call this correspondence ADS-CFT, anti-de Sitter space, and conformal field theory. Don't go into technical details. Just remember, it's a mathematical bridge between volume and surface, between three dimensions and two. But why is all of this necessary? Why are physicists so excited about this idea? The fact is that modern physics faces a profound problem. We have two great theories, two pillars on which our understanding of nature rests. There is Einstein's general theory of relativity, which perfectly describes gravity, the curvature of space-time, the motion of planets and galaxies, and the expansion of the universe. And there is quantum mechanics, which just as perfectly describes the world of atoms and particles, the behavior of electrons in atoms, the transformations of elementary particles, all the forces of nature except gravity. Both theories are incredibly accurate. Both are supported by thousands of experiments, but they are incompatible. When we try to apply both theories at the same time to objects that are both very small and very massive, like black holes or the birth of the universe, the maths explodes. The equations produce infinities, absurd results. We need a new theory that unites gravity and quantum mechanics. Physicists have been looking for it for over a century. And so, the holographic principle offers hope. It shows that perhaps the conflict between these theories can be circumvented by looking at the problem from the other side. If three-dimensional gravitational theory is equivalent to two-dimensional quantum theory without gravitation, then we can solve complex gravitational problems, translating them into quantum language where gravitation does not exist and the problems disappear. Imagine that You are standing on the shore of a lake on a windless day. The surface of the water is absolutely smooth, like a mirror. You see the reflection of the sky, clouds, trees on the opposite shore. This reflection is two-dimensional. It exists only on the surface of the water, but it contains information about the three-dimensional world around the lake. If you could analyze this reflection in enough detail, you could reconstruct a picture of the real world. The holographic principle says something similar. Our three-dimensional world may be a reflection, a projection of information recorded on some cosmic surface. But where is this surface? Where is the boundary of our universe on which all information is recorded? This is a difficult question. Our universe has no visible wall at the edge. It's expanding, and it's expanding at an accelerating rate. Galaxies are moving away from each other faster and faster. Dark energy, a mysterious force whose nature we don't know, is stretching the very fabric of space. And the mathematics that Maldacena used for his correspondence works for a special type of space, so-called anti-de Sitter space, which doesn't behave quite like our universe. In anti-de Sitter space, there is a boundary, a distant but quite definite surface on which all internal information can be written down. Our universe, on the contrary, is rather like de Sitter space. It is expanding and has no clear boundary. This means that the direct application of the holographic principle to our reality remains questionable. Physicists are working on this, trying to generalize Maldacena's ideas to more realistic models of the cosmos. But even if our universe is not quite holographic in the literal sense, the idea itself has opened up new ways of thinking, new ways of attacking old problems. And there is something deeply philosophical, almost mystical, about this theory. The idea that the depth of reality may be an illusion, that the dimensions in which we live may not be fundamental properties of nature, but only a convenient way of describing something simpler and stranger at the same time. Lying in your bed, you probably feel your eyelids getting heavy. Your breathing becomes deeper, slower. Thoughts begin to float, to lose their clarity. And in this half-dream, between wakefulness and sleep, maybe it's easier to accept this strange idea, that the world around you is not quite what it seems, that reality has layers, levels of description that can be completely different from each other, and yet all equally true. Physicists like to talk about the beauty of mathematics. There is something aesthetically pleasing about an elegant equation, a theory that explains many phenomena with one simple principle. The holographic principle has that beauty. The idea that a three-dimensional, complex, three-dimensional reality can be encoded on a flat surface has an almost poetic sound. It's like a good novel in which every detail matters. Every character is connected to the rest by invisible threads, and only in the finale do you see the full picture. Albert Einstein, we will talk more about him later, liked to say that the most incomprehensible thing about the world is that it is comprehensible, that the universe is governed by laws that we can discover and understand, that chaos on the surface hides order at the base. The holographic principle is another example of this amazing property of nature. The apparent complexity of a three-dimensional world can hide a simpler, more fundamental two-dimensional description. But let us step back for a moment to the very origins of this marvelous idea, to the theory that became the foundation for the holographic principle. String theory. Imagine a violin. When the bow touches the string vibrates, and this vibration produces sound. Different modes of vibration produce different notes. The same piece of metal or vein stretched between 2 points can sing hundreds of different voices depending on how it vibrates. String theory suggests something similar, but on a scale unimaginably small, on the edge of what it even makes sense to call size. According to this theory, everything in our world, every particle, every atom, every quantum of energy, is actually a tiny vibrating string. Not a point in space, as we were taught in school, but a one-dimensional object, a loop or segment vibrating at frequencies so high that our best instruments cannot detect them. An electron is a string vibrating in a certain way. A photon of light is another string with a different vibration. Quarks, neutrinos, all the fundamental building blocks of matter are just different notes that can be produced by the same basic entity, the same string. The beauty of this idea is mesmerizing. Instead of a zoo of dozens of different particles, each with its own properties and rules, we get a single bass. One string, one instrument playing the symphony of the universe. And what's more, string theory naturally includes gravity. One of the modes of vibration of the string corresponds to the graviton, a hypothetical particle carrier of gravitational force. This is the unification theory that physicists have been looking for. Quantum mechanics and gravity finally brought together into one consistent picture. But there is a nuance. String theory only works if space has not 3 dimensions, but many more. 9, 10 with time, or 11 in some versions. Extra dimensions, invisible to us, coiled into tiny shapes so small that even the most powerful particle accelerator can't probe them. Imagine a garden hose. From afar, it looks like a one-dimensional line, but an ant crawling along its surface knows that the hose has another dimension. a circle around it. So too, the extra dimensions of string theory exist at every point in our space, but coiled up so tightly that we don't notice them. It was within the framework of string theory that Juan Maldacena discovered his famous correspondence. Strings vibrating in a volume of space turned out to be mathematically equivalent to a stringless theory living on the boundary of that space. Holography emerged not as a philosophical metaphor, but as a rigorous mathematical statement that grew out of an attempt to understand quantum gravity. And this is where the story takes an unexpected turn. Because Einstein, the great Albert Einstein, back in the 30s of the 20th century, fumbled with two ideas that decades later would turn out to be related to the holographic principle in a most surprising way. In 1935, Einstein and his young colleague Nathan Rosen published a paper in which they showed that the equations of the general theory of relativity allowed for the existence of strange objects, bridges in space-time, wormholes. Imagine a piece of paper on which 2 points far apart are drawn. To get from one point to the other, across the surface of the sheet, you have to travel a long way. But what if you bend the sheet so that these dots are next to each other and pierce the sheet through? That would create a tunnel, connecting two distant regions of space directly. A wormhole is something like that, but in four-dimensional space-time. Einstein and Rosen did not believe that such objects really existed. For them, it was a mathematical curiosity, an oddity of equations. But the idea remained, and physicists continued to ponder it. Wormholes became popular in science fiction as a way to travel between stars, or even between universes. In reality, the problem is that these tunnels are highly unstable. They collapse almost instantly unless they are propped up by something with negative energy, exotic matter that we don't know how to create, and don't know if it even exists. In the same year of 1935, Einstein, together with Boris Podolsky and Nathan Rosen, published another famous paper in which they described a phenomenon that Einstein himself called spooky action at a distance: quantum entanglement. The idea is this: two particles can be entangled in such a way that measuring the state of one instantly affects the state of the other, even if they are at opposite ends of the universe. No signal is transmitted. No information is transferred in the classical sense, but the correlation is there. If you have a pair of entangled electrons and you measure the spin of one, you find that it's pointing up. Then you instantly know that the spin of the other is pointing down, even if the second electron is in a different galaxy. Einstein was concerned. He believed that quantum mechanics was incomplete, that there must be some deeper mechanism, hidden variables behind these strange correlations. But experiments had proved time and time again that quantum entanglement was real. The world works exactly as strangely as quantum theory predicts. And so, in the year 2013, almost 80 years after Einstein's work, several physicists came up with a heady hypothesis. What if wormholes and quantum entanglement are the same phenomenon? What if each pair of entangled particles is connected by a tiny wormhole in the depths of space-time? The formula is simple and elegant. ER equals EPR. Einstein-Rosen equals Einstein-Podolsky-Rosen. Wormholes equal entanglement. This sounds like madness. But again, the maths suggests it could be true. If two black holes are entangled in a quantum way, then there could be a wormhole within them, connecting them. And if this idea is true, it has fundamental implications. Space-time, the very fabric of reality, may arise from quantum entanglement. Geometry may not be primary, but derived from quantum correlations. Imagine a spider's web. Each thread connects 2 points, creating a web. The strength of the connections, their number and arrangement determine the shape of the web. Maybe space-time is like such a web, where the threads are quantum entanglement between elementary components of reality, and the shape of the web is the geometry we perceive as space, distance, gravity. This takes us very far away from an intuitive understanding of the world. We used to think that first there is a space, an arena where events unfold, and then particles, fields, interactions appear in this space. But perhaps it is the other way round. First, there are quantum correlations, entanglement between some basic elements of reality, and space appears as a consequence of these correlations. If two regions are strongly entangled, they appear close in space. If the entanglement is weak, they are far from each other. You're lying in your bed, and maybe you're getting a little giddy with these thoughts. That's normal. Even physicists who work with these ideas every day admit that they sometimes experience a kind of conceptual vertigo when they try to imagine what it all really means. But back to the holographic principle. If space arises from entanglement, and if information about a three-dimensional volume can be encoded on a two-dimensional boundary, then the question arises, is there any way to test this? Is it possible to perform an experiment that would confirm or deny the idea that our universe is holographic? Physicists have been trying. At the Fermi National Laboratory in the USA, a device called a holometer was built. The idea was the following. If space-time at the smallest scales has a holographic structure, it should be a little blurred, grainy. Imagine a picture on a computer screen. If you look at it from afar, it looks smooth and continuous. But if you get close enough, you see individual pixels. Maybe Space-time is made up of pixels too, just unimaginably small. And this pixelization must lead to tiny fluctuations, a shaking of space at the quantum level. The holometer was designed to capture these fluctuations. A high-precision interferometer capable of measuring fluctuations on scales close to the Planck length. That's about 10 to the minus 35th degree of a meter, the size at which we think the quantum effects of gravity become important. The experiment ran for several years, collecting data, and the result was nothing. No fluctuations, no sign of holographic granularity. Space-time, as far as the holometer could see, was smooth. Does this mean that the holographic principle is wrong? Not necessarily. Perhaps the effects are too weak to be detected even by such a sensitive instrument. Or perhaps our universe really isn't holographic, at least not in a way that could be verified by this method. Absence of proof is not proof of absence, as scientists like to say. But there was another experiment, more recent and more impressive, though of a completely different kind. In 2022, a group of physicists using a quantum Google computer called Sycamore managed to create a quantum simulation of a wormhole. They took a few dozen qubits, quantum bits of information, and programmed them to interact in such a way that this interaction is mathematically described by the same equations as the wormhole in the theory of gravity. It was not a real wormhole, not a tunnel in physical space. It was a hologram of the wormhole existing in the abstract space of quantum states. But as according to the holographic principle, this distinction may not be significant. The quantum state at the boundary and the gravitational picture in the volume are two descriptions of the same reality. The researchers were able to send quantum information to one end of their simulated wormhole and see it appear at the other end, traveling through quantum entanglement between qubits. It doesn't mean we can build a time machine or teleport to the other side of the galaxy. The experiment was conducted in a tiny system of a few dozen qubits, and the wormhole existed only in a mathematical sense. But it was a proof of concept, a demonstration that the ideas of the holographic principle could be realized practically, that the connection between entanglement and geometry was not just abstract mathematics, but something that could be studied in the laboratory, and here, at the border between physics and philosophy, between mathematics and metaphysics, there is a question that has probably been bothering you since the beginning of this journey. If the universe is holographic, if the three-dimensionality of the world around us is an illusion, what does this mean for ourselves? To our consciousness, to our perception of reality? Are we just part of the hologram, flat shadows cast on a cosmic screen? Or is there something more? Close your eyes for a moment and think about how your perception works. You see the room around you, the walls, the ceiling, the objects. But what is actually happening? Photons of light reflect off the surfaces and into your eye, where they are converted into electrical signals that run along nerve fibers to your brain. And there, in the cerebral cortex, in a tangle of billions of neurons, these signals are somehow transformed into the subjective experience of seeing. A sense of depth, color, shape. Your brain has no direct access to the outside world. All it receives are patterns of electrical impulses. And from these impulses, it constructs a model of reality, a three-dimensional simulation of the surrounding space. In a sense, your brain already works like a holographic projector. It takes a flat image on the retina, essentially a two-dimensional picture, although we have two eyes for stereoscopic vision, and reconstructs a three-dimensional world from it. Depth, distance, volume. Some philosophers and consciousness researchers go further and suggest that all of our perceived reality is a kind of hologram projected by consciousness. When you look at an apple lying on a table, you think you see a real physical object out there. But in reality, the image of that apple exists only in your brain, created from electrochemical processes. True reality is a field of energy, waves, and particles interacting according to the laws of quantum mechanics. And the apple as an object with color, texture, shape, is the interpretation that your consciousness imposes on these abstract physical processes. This does not mean that the world is unreal, or that everything exists only in your head. Physical processes occur independently of the observer, but the way we perceive these processes, the form that reality takes for us, is really a kind of projection, a construct of our consciousness. And if that's the case, then the holographic principle in physics resonates with something deep in the nature of perception itself. There is something almost poetic in the way this idea resonates in different areas of human knowledge. Holography doesn't just appear in particle physics and cosmology. It arises in neuroscience when we try to understand how the brain stores memories. It's hypothesized that memories are distributed throughout the brain holographically, so that damage to one part doesn't erase specific memories completely. It just makes them less clear. It's like if you cut a hologram in half, each half still contains the full image, just with less resolution. Holography appears in holistic medicine, the idea that every part of the body contains information about the whole. In reflexology, it is assumed that there are points on the foot or on the ear that correspond to all the organs of the body. How scientific this is another question. But the very idea that the whole can be encoded in parts clearly has an appeal to the human mind. Maybe because it reflects something true about the nature of complex systems, about how information is distributed and organized in the world. But back to our universe, and the question that remains open. Is our cosmos really holographic? Maldacina's mathematics is beautiful and convincing, but it works for an idealized space, for a world that is not quite like ours. The anti-de Sitter space, in which the holographic correspondence is fulfilled, has negative curvature and a well-defined boundary. It is like a horse's saddle, curved one way on one axis and another way on the other axis. And this space is static, or at least behaves very regularly. Our universe is very different. It's expanding at an accelerating rate. Dark energy, a mysterious force whose nature we do not understand, is stretching space faster and faster. Galaxies are scattering away from each other. And in the distant future, in trillions of years, each galaxy will be isolated in its own space bubble, cut off from all others by the expansion of space. Our universe is described by a de Sitter space with a positive cosmological constant, and such a space has no clear boundary on which to record all the internal information. Moreover, our universe is filled with matter and radiation. Stars, galaxies, dark matter, photons of relic radiation left over from the Big Bang. All this makes the real cosmos far more complex than the idealized models of theorists. And it's not yet clear whether the holographic principle can be generalized to such a universe. Physicists are working on it, offering various options, but there is no consensus. Some suggest that the holographic boundary of our universe is a kind of de Sitter horizon, a sphere defined by the accelerated expansion of space. Beyond this horizon, regions of space are moving away from us faster than the speed of light, and we can never get information from them. In this sense, the de Sitter horizon is like the event horizon of a black hole. It is the boundary of what we can know. And maybe all the information about our observable universe is encoded on this horizon. But this is speculative. There is no direct evidence, and there probably never will be. The holographic principle may turn out to be a profound mathematical truth about the structure of the theory of gravity that has no direct observable manifestation in our concrete world. Or maybe future experiments, more sensitive instruments, new ideas will find a way to test this hypothesis. You are lying in the darkness of your room, and maybe it all seems very far from your everyday life. Who cares if the universe is holographic or not? If you have to get up for work tomorrow, if there are real problems, real things to do, real people around you. And it's a fair feeling. The holographic principle won't change your everyday life. Gravity will continue to pull you to the earth. Light will continue to travel at the speed of light. Atoms will remain atoms. But there is another side to it. We live in a remarkable time when, for the first time in history, humanity is able to ask such questions and seek answers not just philosophically, but with the help of rigorous mathematics and experimentation. We can probe the structure of reality at levels unavailable to our ancestors, even in their wildest imaginations. We can discuss the nature of space and time not as abstract concepts, but as physical entities with concrete, measurable properties. And when we do, when we look deep into the structure of the world, we discover that reality is much stranger than it seemed. That common sense, based on medium-scale experience, the world of rocks and trees, people and animals, planets and stars, that common sense fails us when we go to extremes. To the very small, the quantum world, where a particle can be in two places at once, where the observation affects the observed. To the very large, the cosmological scale, where time flows differently at different points in space, where the universe had a beginning and will probably have an end. To the very massive, to black holes, where time stops at the event horizon, where space collapses into itself. The holographic principle is another step in this journey to strangeness. The assumption that the dimensions of space in which we live are not fundamental. That the depth of the world may be an illusion, a convenient but not definitive picture of reality. It's disorienting. It disrupts intuition. But the history of science is full of such moments when intuition turned out to be wrong, and a strange, counterintuitive idea turned out to be right. Imagine how people felt when they learnt that the earth was not flat, but round. It contradicted all their experience. They walked on a flat surface. The horizon seemed flat. How can the earth be a ball if people on the other side don't fall? But of course, they don't fall because gravity everywhere is directed towards the center of the earth. The spherical earth became an obvious truth as soon as the relevant observations and theoretical understanding became available. Or imagine how people perceived the idea that the earth revolves around the sun, not the other way round. After all, we see the sun rising in the east and setting in the west. It's clearly traveling around us. Copernicus's idea that it was us moving and the sun standing still seemed absurd. But mathematics was on Copernicus's side, and eventually mankind accepted the new picture of the world. Maybe the holographic principle is the next step, rethinking what we take for granted. Maybe in 100 years, school children will study that the universe is holographic, with the same calmness with which they study today, that the earth revolves around the sun. Or maybe the idea will turn out to be a false trope, a beautiful mathematical construct with no relevance to the real world. Time will tell, but regardless of whether that particular hypothesis is correct, the process itself, the process of questioning, exploring, building models, and testing them, is what makes us human. It's what sets us apart from other animals. The ability to question not only how to survive until tomorrow, but what is the nature of tomorrow itself, the nature of time, space, existence. There is a line attributed to the ancient Greek philosopher Socrates. The unexamined life is not worth living. Perhaps that is too categorical. Life has value in all its manifestations. But there is something special in trying to understand, in seeking to look beyond the veil of the ordinary and see the deeper patterns underlying it. And the holographic principle, this strange, dizzying idea that our three-dimensional world could be a projection of two-dimensional information, reminds us that there is still a lot we don't understand, that the universe holds mysteries waiting to be discovered, that behind every answer lies new questions, deeper and more intriguing, lying in the dark, in the silence of the night, when the outside world is quiet and you are alone with your thoughts. It is easier to feel this strangeness of being. During the day, we are immersed in business, in worries, in the flow of events. The world seems solid, reliable, understandable. But at night, in this special silence between sleep and wakefulness, the boundaries of reality become more shaky. And maybe it is in such moments that we are closest to the truth, to the realization that the world is not quite as it seems. Physicists working on the holographic principle often talk about a feeling that is hard to put into words, about how maths leads them in directions they themselves never expected, how equations begin to tell stories that seem too strange to be true, but too beautiful to be false. There is something almost mystical about the way abstract symbols on paper or on a computer screen can reveal depths of reality that are inaccessible to direct observation. Remember how we started this journey, with black holes and the paradox of information, with the question, where does information go when it falls over the event horizon? And the answer that physicists came up with was revolutionary. Information doesn't go anywhere. It remains on the surface, on the event horizon, encoded there in a way that we are only beginning to understand. Each bit of information corresponds to a specific area on the surface of the black hole, and this area has a size related to the Planck length, the fundamental quantum of space. The Planck length is about 10 to the minus 35th power of a meter. It is so small that if an atom were to expand to the size of the solar system, the Planck length would be about the size of a human hair. At such scales, the very concept of distance begins to lose meaning. Space-time becomes frothy, quantum fluctuations so strong that the geometry is constantly changing, boiling up, and calming down again. This is the realm of quantum gravity, where the laws that work in our familiar world cease to apply. And it is at this level, at the level of Planck scales, that the holographic principle should manifest itself most vividly. If space really consists of discrete pixels of information, then the size of these pixels should be related to the Planck length. Each such pixel is a quantum bit, a qubit of reality. And everything that happens in our three-dimensional world, every movement of a particle, every interaction, every thought, in every consciousness, all this can ultimately be described as an interweaving, an evolution, a dance of these basic quantum bits on some fundamental two-dimensional surface. It is similar to the way a digital photograph is stored in a computer's memory. The image may show a deep, three-dimensional landscape, mountains going off into the distance, clouds at different heights, trees in the foreground. But all this information is encoded in a sequence of ones and zeros in a one-dimensional memory array. The physical structure is a flat, one-dimensional sequence. But the information describes a three-dimensional scene. And when the computer decodes this information and displays it on the screen, we see depth, volume, space. Maybe our universe works in a similar way. The fundamental structure is flat, two-dimensional, or even more reduced. But the information encoded in that structure unfolds to us as a rich, complex, three-dimensional world with time, causality, history. We are characters in this unfolding description, patterns in the information field that have learned to realize themselves. This raises deep questions about the nature of consciousness, about free will, about meaning. If we are holograms, does that mean we are less real, less important? I think no. A pattern remains a pattern, no matter what substrate it is recorded on. A Beethoven symphony is not made less beautiful by the fact that it can be recorded as vibrations in the air, or as grooves on a vinyl record, or as a sequence of ones and zeros on a digital medium. Music is a pattern, a structure, a relationship between elements. And it is this pattern that brings beauty and meaning. It's the same with us. If our existence is a pattern of information recorded on a cosmic hologram, that doesn't make us an illusion. The pattern is real. The information is real. The experiences we have, joy, sadness, love, fear, wonder, are all real processes that occur in the real world, even if the fundamental structure of that world is not organized in the way we intuitively imagine. There is an old philosophical riddle. If a tree falls in the forest and no one hears it, does it make a sound? The answer depends on what we mean by sound. If sound is air vibrations, then yes, the tree creates these vibrations independently of the observer. If sound is a subjective sensation in the mind of the listener, then no, there is no sound without the listener. The holographic principle offers a similar duality. There is a fundamental description of reality at the holographic boundary: abstract, mathematical, two-dimensional. And there is an emergent description in the volume: familiar, intuitive, three-dimensional. Both descriptions are true. Both describe the same reality from different perspectives. The word emergent is the key word here. Emergent properties are properties that arise at the level of the system as a whole, but are not inherent in its individual parts. Consciousness, for example, is emergent with respect to neurons. No single neuron possesses consciousness, but trillions of neurons connected in a certain way give rise to subjective experience, thinking, and self-consciousness. Fluid is emergent with respect to molecules. An individual molecule of water is not wet or flowing, but billions of molecules together create the properties we call fluidity and wetness. Maybe space-time itself is emergent. It arises from a more fundamental level of description, where there are no familiar concepts of distance, duration, causality. At this basic level, there are only quantum states, entanglement, information correlations, and space, time, gravitation. The whole classical physics are emergent phenomena arising when we look at the system as a whole, at the macroscopic level. It's a radical idea. It overturns our understanding of reality. We used to think that first there is space and time, an arena, a stage on which the play of nature unfolds. And then the actors, particles, fields, interactions appear on this stage. But the holographic principle and related ideas suggest that the order is reversed. First, there is information, quantum correlations, entanglement, and space and time arise from this information as emergent structures. Physicists continue to explore these ideas. They are building models in which they try to show exactly how space-time can emerge from quantum information. They are studying how small changes in entanglement affect the geometry of space in holographic models. They are looking for experimental signatures that might confirm or refute these hypotheses. This is hard work at the cutting edge of human knowledge, where maths and physics are intertwined with philosophy, and where every step forward opens up new horizons of the incomprehensible. But for you, lying in your bed on this quiet night, perhaps it's not the technical details that matter, but the overall message. The message that the world is full of mysteries, that behind the familiar surface of things, there are depths we are only beginning to explore. That reality is richer and stranger than we can imagine, and that the human mind, that amazing tool, is capable of looking into these depths, of asking questions that seem meaningless at first glance, and of finding answers that change the way we look at everything. The holographic principle reminds us of the importance of perspective, that the same situation can be described in different ways, and different descriptions can be equally true. The seemingly insurmountable conflict between quantum mechanics and gravity can be resolved if we learn to look at the problem from a different angle. This is a lesson not only for physics, but for life. Sometimes, to understand a situation, we need to change our perspective, to look not from the inside, but from the edge, not from the perspective of the individual part, but from the perspective of the whole. And there is something comforting about the idea of wholeness inherent in the holographic principle, that each part contains information about the whole, that the universe is not fragmented into isolated pieces, but is a connected unity where everything affects everything, where the division between here and there is ultimately contingent. We are not isolated in our separate corners of space. We are all parts of one huge pattern, one cosmic hologram, if you will. And maybe there is a beauty in that. It's getting close to bedtime. Your breathing becomes more even. Your thoughts slow down, dissolve into a pleasant slumber. And may this night bring you peace of mind. May your dreams be light, filled with that special sense of wonder at the infinity of the world. We have come a long way today, from black holes to the holographic principle, from string theory to quantum entanglement, from mathematical abstractions to philosophical reflections on the nature of reality. And although we didn't get definitive answers, science rarely gives definitive answers, we touched something important. The amazement that comes when you realize how little we know and how much remains to be discovered. That awe at the complexity and beauty of the universe, which continues to surprise us at every new level of exploration. Sleep well, my dear listener. Let the stars above your head, whether they are real in 3 dimensions or projections on a cosmic screen, shine softly on you. Let space-time, emergent or fundamental, lull you with its quiet flow. And remember, in this vast, mysterious, perhaps holographic universe, there is room for wonder, for questions, for searching, and that search continues. Every night, when someone somewhere is looking up into the sky and asking eternal questions. Every day, when scientists in laboratories and at desks try to solve another mystery of nature. Good night. Until next time, when we will once again journey to the frontiers of the known, where science meets wonder, where mathematics whispers poetry and physics tells tales. Strange, wonderful, but perhaps true tales of how our world works. Close your eyes, breathe deeply, and may this night bring you peace and beautiful dreams. See you again in the silence of the night, in the comfort of darkness, in that special space between reality and dream, where everything is possible, and where maybe the border between illusion and reality is thinner than we think. Good night.